So what we're going to be doing is looking at chemical reaction writing and a review of the basic types of chemical reactions. The 5 major types of chemical reactions are combustion, synthesis, decomposition, single replacement, and double replacement. And some of these reaction types have different names, such as double replacement can sometimes be called a metathesis reaction, but overall it means the same thing and will have the same features. So let's go ahead and look at each of these individually. So combustion reactions. Combustion reactions occur when you burn a substance in the presence of oxygen, and these typically produce heat. Now, if we're actually looking at the components of the reaction, we'll typically have some substance, we'll have oxygen, and then we'll have subsequent products. And your products are going to have oxygen in them. So below here we see a hydrocarbon that's being reacted with O2 to give us CO2 and H2O. And we'll talk about the details of those, the different types of reactions that fall under the combustion category on this next slide. So when we're predicting a combustion reaction, we know that our products are always going to contain oxygen. So if you look here at this first combustion reaction, you'll notice that we have oxygen here and oxygen here in our products. Also, if you look at the one below, notice that you have a metal oxide, so you have oxygen present in your products there as well. Okay, so all of your products are going to contain oxygen. Now, when you're combusting a hydrocarbon, so a hydrocarbon, guys, remember, is anything that contains hydrogen or carbon, you're going to end up with 2 distinct products, which is CO2 and H2O. Those will always be your products. So if you have a hydrocarbon and you start with that and you have oxygen, you know that your 2 products are always going to be CO2 and H2O. When you're combusting a metal in the presence of oxygen, you know you're going to get the ionic formula for the metal oxide present. So this is just a basic way to predict your combustion reaction products. And remember that you're always looking for the presence of oxygen in those final products, as well as the diatomic form of oxygen as a reactant. This brings us to our next chemical reaction type, known as synthesis. So when I hear the word synthesis, I think of something being made or synthesized in a lab or created. Okay, so a synthesis is when you take a combination of 2 or more substances to form a new compound. Okay, in synthesis reactions, you're only going to typically have one product. Okay, so notice we have the A, B, those two come together, those 2 reactants come together to form a new compound, a single product. Okay, so synthesis reactions have 2 or more substances that give you a single product. So if you guys go online onto YouTube and you look up the reaction between sodium and chlorine, you'll see a really nice synthesis demo. You'll actually see the formation of sodium chloride from the elemental sodium metal, okay, and your chlorine gas. It's actually really kind of pretty. It's not a demo that I would ever do in class, but it's an awesome video. So go ahead and look it up on YouTube if you're interested. So how are we going to actually predict products when it comes to synthesis reactions? Okay, in synthesis reactions, for ionic products, okay, typically if we're starting with a metal and a nonmetal, okay, you can just take the individual elements, because we know metals and nonmetals coming together will give us an ionic compound. We take those 2, right, and we use the cross-down method. So Al forms a +3, Cl forms a -1. We cross those down, and that gives us AlCl3. Okay, so that allows us to predict our product, because in this case we have a metal, okay, elemental metal, and diatomic chlorine, which is how it naturally occurs in its elemental state. And since we have a metal and nonmetal, we know we're going to get an ionic product. So this is a way to predict your synthesis reaction products. Okay, when you're dealing with covalent compounds, though, it becomes extremely difficult to tell. It depends on lots of different features. So the reality of it is, with covalent compounds, you're going to have to base that on basically your number of products. Okay, so if you've taken 2 different materials and you get a single product, you know that you're going to end up with a synthesis. Now, synthesis is the creating of a single product by combining substances. Decomposition is just the reverse. Okay, so decomposition is basically the breakdown of a compound, so a single substance, into two or more substances. Okay, so in this case, to identify that you have a decomposition reaction, you're going to be looking for the fact that you only have one reactant. Okay, and a really nice decomposition demo, this one is one that you could do on your own with some peroxide and simple yeast. And it is one that I would normally do in class, but since we're doing this on videos, basically H2O2 decomposing into H2O and O2. Notice you start with a single reactant and multiple products. Okay, this is known as a elephant toothpaste demo, and it's readily available on YouTube. So if you'd like to check that out, you should feel free to do so. Okay, so for decomposition reactions, basically the prediction of products is pretty straightforward. Okay, if you have a binary compound, so for instance potassium and bromine, okay, you would just take those and break them down into their simple elements. So we know potassium occurs as just a K atom, right? Metals are able to do that. Okay, they don't necessarily have to be in compounds to be stable. And bromine, we know that when it's by itself, we know that it occurs as a diatomic. So we could just predict our products in this manner. So single replacement reactions is a situation in which one element is going to replace another element that's found inside a compound. Okay, so usually the metal is going to be replacing another metal, or the non-metal will replace another non-metal. Okay, so in this case, A here is going to go ahead and replace B to give us AC. Notice this, okay? And notice that B is now by itself. So basically, you take an element, okay, and that element is going to replace one of the components of a compound. Okay, and then you'll end up with a different element, okay, and subsequently a new compound. Right, so single replacement, one thing outside of a compound is replacing another thing in a compound. So here's an example of a single replacement reaction. We have copper, elemental copper here. We have silver nitrate. And what's going to happen here is that the copper is going to replace the silver, okay, to now give us copper nitrate and elemental silver. Okay, so we've already looked at these things. We've looked at the activity series and things of that sort. That's what dictates if this will actually happen or not. So we talked about that in terms of chapter 20. But this is basically a single replacement reaction. Okay, so how are we going to predict products? Well, first of all, okay, when you have a compound and a single element, that's a good indicator that you're probably going to be able to have a single replacement reaction happening. And normally, obviously, that single atom is going to be a metallic element, and you're going to have an ionic substance, okay? Ionic compound. Those are usually good indicators. Now, in a more advanced set, you'd have to use the activity series to make sure that these can actually swap places, okay, that would actually happen, right? But for the sake of right now, okay, assuming that, it will happen, we know that our iron is going to replace our copper to give us iron sulfate, okay, iron 2 sulfate, I guess, let's be more specific, okay, and copper solid is what we have as our product. Okay, so basically your metal is going to replace another metal, and basically your non-metal will pretty much just stay the same. It'll just correspond or be connected with a new element. So double replacement reactions. A great example is the mixing of barium chloride with sodium carbonate. Okay, this gives us our barium carbonate precipitate here. If you guys want to check this out online, you can totally look it up on YouTube. It's available for your viewing pleasure. It's actually very beautiful. We have two clear solutions, we mix them together, and we get this yellow precipitate of barium carbonate. So let's go ahead and talk about what a double replacement reaction is and how it actually works. In double replacement reactions, the ions in the two compounds, so A, B, and C, D, are going to change partners, right? Okay, so in this case, we're going to be changing A and C, okay? And basically, they just swap, and they form two new unique compounds. So basically, you can look at it as the metals swapping places if you have two ionic compounds, or you can look at it as the two nonmetals swapping places. Either way that you look at it, it doesn't really matter, but you're going to end up with two new compounds. So basically, they've changed partners. If you compare this to, dancing, if you and your friend are dancing with your girlfriends, and then you guys decide, okay, hey, we're going to dance with each other's girlfriends. Now you've shown a double replacement setup. So that would be kind of an analogy to use. So let's go ahead and look at predicting. So if we look at a chemical reaction, a double replacement reaction, we need to first of all look at the fact that we are going to have two ionic compounds basically set up here. Now with those two ionic compounds, we are going to need to figure out, once we decide how they've swapped, which you can see here, they've swapped their potassium and lead metals, okay? After you figured that out, you need to actually think about, okay, am I going to get a precipitate? Okay, am I going to get something to crash out of solution? So if you guys look here, notice that one of the products is a solid, while the other is aqueous. If both of them remain aqueous, so if there's no precipitation, you're going to have to consider that no reaction has occurred. So how do you do that? How do you figure that out? Well, there's something called solubility rules. And solubility rules are basically things that you're going to have to memorize. There's a chart after the next slide that we're going to be looking at that you actually need to look at and get comfortable with and basically memorize in order to be able to make accurate assessments. Finally, predicting the products. Okay, so the first thing you guys are going to have to make sure that you're doing, okay, is that you swap your negative ions in the two compounds that you have. So two compounds, okay, two ionic compounds, you're going to swap those out. Okay, and guys, one product, remember, always has to be insoluble. Okay, so you're either going to get a precipitate, so lead iodide would be a great example. Or also, sometimes your product can leave as a gas. The gas is actually usually a lot more rare or less likely to be the type of double replacement that you'll be looking at. But just be aware that if gas is able to leave the solution as a product, then you have a form of a double replacement reaction. So in situations where the solubility rules don't indicate that you can actually form a precipitate, you would indicate subsequently that there is no reaction. Okay, so let's go ahead and let's look at the solubility table. So as you can see here, here are some simple solubility rules. There's lots of different tables. Basically, they say the same thing. Some are more in depth. This is a very simple one, but it's a very nice place to start. Okay, so how do you actually use the solubility rule table? Okay, well, the first thing here is you look at the ion. So NaNO3 might be a substance, right? Okay, and I'm going to look at this, and I want to determine if it's soluble or not. Would it dissolve in water or not? Okay, and so what I need to do is I need to, first of all, look at my substance and find the component in that ionic compound that actually shows up on the solubility chart that I have, or the solubility rules that I have memorized. Okay, so NO3 in this case is definitely here, and if you look down the list, if you continue down the list, okay, sodium is also present. Okay, so either way that you go about answering this, they're both going to be sufficient. Okay, so if we look at this, it says Na, right? Let's look at Na+. Okay, that's what I have present in this compound. It says that they are soluble. Okay, so this is the solubility. So any compound containing sodium should be soluble. Now we go to the exceptions list. Okay, are there any exceptions? No. So what that means is that sodium chloride, sodium iodide, sodium fluoride, any example where sodium and an anion are present, that you should have a soluble substance. Okay, and if you come up here and you look at NO3-, the nitrate anion, okay, you notice that solubility is indicated straight away and also no exceptions. So this is definitely a soluble molecule. So if I take sodium nitrate and I put it into water, I'm definitely going to get a solution. Now let's go ahead and look at another example. So here we have silver chloride, okay, and what you should notice initially, after you've decided what ions are present, obviously we have Ag+, okay, and Cl-, you should notice that if we go over here to the left-hand side and look at the table, we don't actually have Ag present as an ion we can look up, okay, but we do have the chloride ion. So let's look at chloride. So the chloride ion indicates here, it's indicated that compounds containing the chloride ion are soluble. There are exceptions, however, okay, except for silver, mercury, and lead ions. Okay, because of that, we know that AgCl is going to give us an insoluble compound. All right, because the silver is on the list of exceptions, we know that that compound will be insoluble in water. Okay, so that's just the basic way that you utilize solubility rules and solubility tables. I'd suggest you guys look at this table. I'd also suggest that you guys memorize the one in your book, get extremely comfortable with both sets, and make sure that you're able to identify if you can get a product that is a precipitate, so that you can determine if you have a double replacement reaction. Otherwise, you're just going to be guessing and you may end up with the incorrect answer. So go ahead and spend some time memorizing it, and good luck. Okay, so let's go ahead and let's do some practice here, right? So let's look at what we have present, okay, on the left-hand side in order to go ahead and predict our subsequent products. So notice, what do we have here? C4H10. C4H10, automatically you guys should think, oh, that's a hydrocarbon. Okay, then I have oxygen. Okay, so when I have hydrocarbon and oxygen, I am most likely going to get a combustion reaction. And I know that when I combust a hydrocarbon, in the presence of oxygen, I get CO2 and H2O. Okay, so this is going to be a combustion reaction, and these are my subsequent products. Obviously, you would go ahead and balance, but CO2 and H2O give you your combustion products. Okay, so in this next example, notice that we have two elemental forms of two element types. Okay, so a fair amount of the time when you have that type of setup, you're going to be getting some sort of synthesis, because you're taking your simplest form of elements and you're putting them together to form a compound, right? So in this case, we're just going to go ahead and say that we have PBS, okay, as our product. We put them together. That's a completely legitimate option, okay, and this is going to be a synthesis reaction. So let's go ahead and let's look at this next one. Well, notice that we have KClO3 as a single reactant. Okay, so when we have a single reactant, we know that we're going to break something down. We're going to take something that's already built up and put together and put it into smaller components. So this is going to be a decomposition reaction. So deciding what products you're going to get is somewhat difficult here. Why? Because we don't have a binary compound. Okay, so but we do know that potassium and chlorine will come together, right? Potassium and chlorine will come together to give you KCl, okay? And we know that oxygen, in its most simplistic form, is O2. Okay, so predicting your products here would have been a lot more difficult because you're not starting with a binary compound. But the reality of it is that you could come up with some combination of KCl, maybe potassium, chlorine, and oxygen gas. Those could have maybe been options that you may have predicted. As I indicated, these would not be as easy to predict, but usually when you have oxygen as a portion of your initial compound, a lot of times it'll become elemental oxygen, and the metal and non-metal will break down into their prototypical salt. But as I said, this one wouldn't have been super easy to do, but you could have at least come up with some sort of breakdown. So this is your decomp. Okay, reaction. All right, let's go down here to this next one. What do you notice initially? Okay, you notice automatically that you have a single element by itself and you have a compound. Okay, that single element all by itself is a metal, and the compound you have in is an ionic compound. So this should scream to you single replacement. Okay, so in this case, guys, FeNO3, right? They're going to swap places. Okay, plus Cu. Right? So this is a single replacement reaction. Very, very straightforward. So let's go ahead and let's look at our final reaction. Okay, you should initially or immediately notice that you have two ionic substances. Okay, you should go ahead and swap the places. Okay, so swap your lead and swap your potassium. So we end up with PbI2. Okay, and we end up with KNO3. Right, so we get a double replacement reaction. But how do we know for sure that we have a double replacement reaction? Okay, well, we talked about earlier that nitrates are all soluble, so we know that this is an aqueous setup here. Okay, and we would have to have memorized the fact that halides in the presence of lead are going to give you precipitates. Okay, so you would have had to double check and make sure that you're getting a precipitate of some sort in order to establish this as a double replacement reaction. So this is just some of the thought process and some of the think tank way to go and approach these. It's not easy, but with extra practice, you'll be able to be proficient. So good luck.